Hello, everyone, and welcome to this explainer. We're jumping right in today because we have a fantastic topic to cover. I'm absolutely thrilled to have you here as we dive into U07L04, Proportional Relationships Mini Project Video Overview. Whether you're wrapping your head around this concept for the very first time, or you're just looking to seriously level up your understanding of how quantities relate to one another, you are in exactly the right place. We're going to break down the math step by step using some really revealing data and clear evidence. Basically, we are turning into mathematical detectives today to figure out what actually makes a relationship proportional.
Okay, here's our quick roadmap for mastering proportional relationships today. 1. Welcome to U07L04. 2. Misconception, the table trap. 3. Evidence, proving the pattern. 4. Application, mini project challenge. And finally, number 5, transfer, test your knowledge. Let's get right into it.
Starting with Section 2, Misconception, the table trap. Let's kick things off by setting up a really common mathematical mystery that traps a ton of students when they first start analyzing data.
So here's a big question to chew on. Does a data table tell you everything? Imagine you're looking at a table showing two quantities. You divide the numbers in the first row and boom, you get a quotient. You divide the second row, you get the exact same quotient. Third row matches too. So, is finding matching quotients in a few rows of a data table absolute, definitive proof of a proportional relationship? Well, most people would instantly say yes, for sure. But we actually need to look a little closer.
To debunk this table trap, we have to look at this direct insight from our instructional material, which states, it is not possible to determine that a relationship is certainly proportional just from examining a table. And why is that? Because there might be other pairs of values not shown on that specific table that are related by a totally different unit rate. Those hidden, unlisted values could completely break the pattern. A table can definitely tell us a relationship might be proportional, or it can prove it's definitely not proportional. But a limited table all by itself, it just can't give us absolute certainty.
Let's move on to Section 3, Evidence, proving the pattern. If a table isn't the ultimate proof, then what is? We need to look at the hard evidence.
Let's contrast two different scenarios side by side to see how this works. We're looking at the prices for smoothies at two different spots, Smoothie Shop A and Smoothie Shop B. Take a look at Shop A first. For an 8-ounce smoothie, the price is $6. Divide 6 by 8, and you get 75 cents per ounce. Okay, what about the 12-ounce? It's $9, which still comes out to 75 cents per ounce. So Shop A maintains a strict 75 cents per ounce unit rate across the board. But then, glance over at Shop B. An 8-ounce smoothie is $6, starting off the same at 75 cents an ounce. But a 12-ounce smoothie is $8. Divide 8 by 12, and suddenly that rate drops to about 67 cents per ounce. The unit rate actually varies.
This brings us to a crucial point. The only thing that proves a relationship is completely proportional is an equation in a very specific format. That equation is y equals kx. In this setup, y and x are our two related quantities, and k is what we call the constant of proportionality. Think of k as the unbreakable rule of the relationship. It is the exact same quotient you get every single time you divide y by x. If you can confidently write an equation in this exact form to represent the entire situation, well, then you have your definitive proof.
And this brilliantly illustrates how Shop A fits that y equals kx format perfectly. We can write their pricing model out like this. P, representing the price in dollars, equals 0.75 times S, representing the size in ounces. In this scenario, 0.75 is acting as our constant of proportionality, our K. No matter what size smoothie you order from Shop A, you just multiply the ounces by 0.75 to get the price. The rule literally never changes.
Let's quickly summarize the hard evidence here. Shop A has a constant rate of 75 cents per ounce, which means we can write an equation for it. Shop B, however, has changing rates of 75 cents, 67 cents, and 62.5 cents. I really want to emphasize this. Dividing related quantities to find the unit rate instantly reveals when a relationship, just like Shop B, is definitively not proportional. The very second that quotient changes from one row to the next, the investigation is over. It is absolutely not a proportional relationship.
All right, moving to Section 4, Application Mini Project Challenge. It's time to take all this theory and apply it to a real-world data set.
For your mini project data analysis, you're going to follow a very specific set of steps to ensure your mathematical investigation is super rigorous. Step 1, you'll examine the data and decide if the relationship is proportional. Step 2, you must justify your decision with clear mathematical evidence. Step 3, you'll complete a data table and a conceptual graph based on the situation. Step 4, if the relationship allows for it, you'll write an equation. And finally, Step 5, you'll state a clear, evidence-based conclusion. Let's actually practice this together right now.
Okay, here's your scenario. Imagine you're visiting a state park. The entrance rule is this. It costs a flat $6 fee per vehicle, plus an extra $2 for every single person inside that vehicle. Let's see how the total costs shake out in this data. For 2 people, it's a $6 vehicle fee plus $4 for the people, totaling $10. For 4 people, it's the $6 fee plus $8 for a total of $14. And if you pack 10 people in, it's $6 plus $20, coming out to a $26 total.
So here is my challenge for you. Is the relationship between the number of people in the vehicle and the total entrance cost proportional? To figure this out, I want you to mentally find the cost per person for each row. We need to see if those quotients are equal. Think about it this way. If everyone in the car split the bill evenly, is everyone paying the exact same share regardless of how packed the vehicle is?
Let's look at the math. If 2 people pay $10 total, they're paying $5 per person. If 4 people pay $14 total, you divide 14 by 4 and they're paying $3.50 per person. And if 10 people roll up in a big van and pay $26, they're only paying $2.60 per person. Because those unit rates, $5, $3.50, and $2.60, are all totally different, the math proves the state park fee lacks a constant of proportionality. So our conclusion is firmly that this relationship is not proportional. You literally cannot write a simple y equals kx equation for this park entrance fee.
And now for our final act, Section 5, Transfer. Test your knowledge. This is where you get to prove you've fully mastered the concept by transferring what you know to a brand new scenario. We're going to look at the apples and pizza cool-down challenge, straight from the source material. We have 2 different purchasing situations here, and you need to put your mathematical detective hat back on to figure out which one of these follows the rules of proportionality. Here's the data displayed side by side. On the left, we've got the cost of apples based on their weight in pounds. 2 pounds cost $3.76, and 3 pounds cost $5.64. On the right, we have the cost of a pizza based on the number of toppings. A 2-topping pizza is $11.99, and a 3-topping pizza is $13.49. I want you to calculate the unit rate for both the apples and the pizza toppings. Just divide the cost by the quantity for each row. What do you notice?
And here is the evidence-based explanation. Let's look at the apples first. $3.76 divided by 2 is $1.88, and $5.64 divided by 3 is also $1.88. The apples have a constant unit rate of $1.88 per pound, meaning this relationship absolutely could be proportional. In fact, because that constant unit rate exists, we can write a perfect equation for it. C for cost equals 1.88 times P for pounds. But what about the pizza? $11.99 divided by 2 is about $6, but $13.49 divided by 3 is about $4.50. The cost per topping changes, meaning the pizza pricing is definitively not proportional.
Well, we've busted the table trap, analyzed smoothie shops, calculated state park fees, and compared apples to pizza. You now have the exact tools you need to demand hard evidence before declaring any relationship proportional. So I'll leave you with this final thought. Take a look around your own life, your hobbies, or even your local grocery store. What data are you going to investigate next to see if a true proportional relationship is hiding right there in plain sight? Thank you so much for joining me for this explainer, and happy calculating.